Welcome everyone. In this video we are going to derive a formula for velocity, horizontal velocity in terms of time using linear drag. So what do I mean when I say linear drag? Well, let me erase this. This simply means that we can represent the drag force, the magnitude of it, as proportional with the velocity, the speed. And if you want to have vector notation, we need to turn this proportionality to an equality. So we put a constant of proportionality, which we call k. Then we have the velocity with the arrow this time. And this will be equal to the force of drag when we put the negative sign, because this is a frictional force and it is going to oppose the motion. That's why there's a negative here. So, how does this help us while deriving a formula for horizontal velocity in terms of time? So, our question is basically, what is v of t? As in every mechanics question, we start by drawing a free body diagram. So, we have the object moving through air, and it is here like this. There will be a gravitational pull on it, mg downwards, and there will be, normally we don't separate forces into their components in free body diagrams, but for this derivation I will do that because I think it is better to do that. So we will have kvx in the horizontal. This is the component of drag force in the x direction if we choose the x like this and the y like that. And the direction of the y, the direction of the drag in the y can change, but let's call it like this, kvy. So in this case, the velocity vector would be something like this, right? Because both of the components of the drag force should oppose the corresponding component of the velocity. So we got this, cool. And now, since we are interested in the horizontal direction, I should put a x here as well. We will simply use Newton's second law for the horizontal. So we will say F net in the x direction is equal to mass times the acceleration in the x direction. And if you wonder how this formula is true, I proved this in a previous video. You can find it from the cards right now, also from the descriptions part. Now, the F net in the x direction is going to be kvx with a negative sign in front. The negative is incredibly important. Please don't forget it. This is equal to mass, and instead of the acceleration in the x, I am going to write the time derivative of the velocity in the x, the component of the velocity. Alright, because this is the definition of acceleration. Now, I want to have vx and dvx on the same side. To be able to do that, I will first multiply both sides by dt. So I have negative dt k vx is equal to m dvx. Now I will divide both sides by m and by vx to get, let's see, we will get negative k divided by m dt is equal to dvx divided by vx. Alright? This is the differential equation that we want to solve. And how can we solve for it? Well, the best way to solve for it is using an integral. So let's take the integral of both sides. And should we do that with a different color? Well, why not? So we take the integral of both sides. We need to decide on our boundaries. We don't need to do this, then we would have a constant c and we can figure it out using initial conditions, but I want to use a definite integral because I think this is easier. So the left boundary is fairly simple. We will start from 0, time starts from 0 and goes up to any time, which we denote by t. On the right, when we are at time 0, this corresponds to the initial velocity, which I will simply call v0. And since this is in the x direction, I will also add the subscript x. And the upper limit will be the velocity function that we're looking for, vx of t. Great. So if we start by solving the left side, we will simply get, using the fundamental theorem of calculus, we will get negative km t evaluated at the boundaries t and 0. So we will simply get this. We don't need the boundaries because when we plug in 0, we get 0. This is equal to, on the right we have dvx divided by vx. This gives, this is basically asking which function has the derivative 1 over x, and that function would be ln of x. However, there is a little nuance, that is, there is an absolute value, because the argument of ln cannot be negative. Alright, that's why we put the negative sign. That's why we put the absolute value. Of course, we don't forget the boundaries vx of t and v0 x. So, if we plug these in, let's do that. We will have ln absolute value vx of t minus ln the absolute value of v0 x. This is going to be using a property of logarithms, ln of the absolute value of vx of t divided by v0 x. Alright. Now let's continue on the new page and let me summarize what we have shown so far. We have negative km t is equal to ln the absolute value of vx of t divided by v0 x, and we close the absolute value. Here now I'm going to just neglect the absolute value because we don't need it for this case. Why don't we need it? Well, vx of t and v0 x will be in the same direction. So whether or not they are, so if one is positive, the other is positive. If one is negative, the other is negative. So we simply can neglect the absolute value. We have ln of vx of t divided by v0 x. Alright, so far so good. Now, and also notice one thing, v0 x cannot be 0. In that case, we would be dividing by 0. And it makes sense that it can't be 0, because if there is no motion in the horizontal, drag force cannot start a motion, right? Friction forces don't start motion, especially kinetic ones. And this is a force associated with motion, so if there is no motion, the force cannot exist, which means it can't start motion. So we see v0 x is not equal to 0, and that correlates with reality. Also, the fact that these vx of t and v0 x have the same direction makes sense because friction, the air drag, cannot change the direction of the motion when the object comes to an instantaneous rest. The force is no longer there, so it stops. Okay, in the vertical case, it is a little different because there is gravity, but for the horizontal, only force is the drag, so there is no change of direction. I just wanted to highlight this. But anyways, let's solve this. So we will raise e to the same power on both sides, and we will get, I'm just going to write the right side first. By the definition of e and ln, this will give us the argument of ln. They are inverse functions. So we have vx of t divided by v0 x is equal to negative k, I forgot to raise it to the power of e. We have e negative km t, And if we multiply both sides by v naught x, we will find the formula that vx of t is equal to v naught x times e raised to the power of negative k mt. And this is the formula. If you want to graph this very basically, to sketch it qualitatively, it would look something like this. So we have the t-axis, we have the velocity. When we plug in 0 for t, e to the power of 0 gives us 1. So the initial value is v naught x. And I am taking v naught x to be positive. Oops, I meant to erase it. So we have v naught x, and this will be decreasing. It is decreasing exponentially. It will decrease in such a manner. There is a horizontal asymptote at t is equal to 0, because as t approaches infinity, the vx function approaches 0, as you can see from the sketch that we have just made. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.